helpful website for transformer protection calculations and wire conduit sizing is electricalcalculations.net. This website offers transformer overcurrent protection calculations covering both primary and secondary protection. It also provides tools for wire size calculation and conduit size calculation. The calculations are based on Article 450.3 of the National Electrical Code. The website is designed with a user-friendly interface and offers quick reference tables. It also allows users to print the results of their calculations. The website supports various transformer connections, including delta-delta, delta-Y, and Y-Y configurations. When performing transformer overcurrent protection calculations, several factors must be considered. These include the transformer's kilovolt-ampere rating, the primary and secondary voltages, and the impedance of the transformer. The primary overcurrent protection is designed to protect the transformer from overloads and short circuits on the primary side. The secondary overcurrent protection protects the transformer from overloads and short circuits on the secondary side. The National Electrical Code, or NEC, provides specific guidelines for selecting the appropriate overcurrent protection devices for transformers. Article 450.3 is particularly relevant. The size of the primary overcurrent protection device is typically based on the transformer's primary current rating. The NEC allows for some adjustments to this value based on the transformer's impedance and other factors. The size of the secondary overcurrent protection device is based on the transformer's secondary current rating. Again, the NEC provides guidance on making adjustments based on specific circumstances. In addition to overcurrent protection, it is also important to properly size the wires and conduits that are used to connect the transformer. The wire size must be sufficient to carry the full load current of the transformer without overheating. The conduit size must be large enough to accommodate the wires and any necessary grounding conductors. The NEC provides tables that specify the allowable ampacity of different wire sizes and the maximum number of wires that can be installed in a given size of conduit. When selecting wire and conduit sizes, it is important to consider the ambient temperature and other factors that may affect the ampacity of the wires. Higher ambient temperatures can reduce the ampacity of wires, requiring larger wire sizes. The type of insulation used in the wires also affects their ampacity. Some types of insulation are rated for higher temperatures than others. Grounding is another important consideration when installing transformers. The transformer must be properly grounded to protect against electric shock hazards. The NEC specifies the requirements for grounding transformers, including the size of the grounding conductors and the methods for connecting them. In addition to the NEC, there may be other applicable codes and standards that must be followed when installing transformers. These may include local building codes and regulations. It is important to consult with a qualified electrical professional to ensure that the installation meets all applicable requirements. The website electricalcalculations.net can be a helpful resource for performing transformer protection calculations and wire conduit sizing. However, it is important to remember that the calculations provided by the website are approximate and should not be used to replace consulting an electrical professional for specific design requirements. Always refer to the NEC and other applicable codes for accurate calculations. For example, consider a 75 kV-ampere transformer with a primary voltage of 480 volts and a secondary voltage of 208 volts. To calculate the primary full load current, divide the kilovolt-ampere rating by the primary voltage and multiply by the square root of 3. That is 75,000 divided by 480 divided by 1.732. The result is approximately 90.2 amps. According to the NEC, the primary overcurrent protection device should typically not exceed 125% of the primary full load current. In this case, 125% of 90.2 amps is approximately 112.8 amps. Therefore, a 110 amp circuit breaker or fuse would be an appropriate choice for the primary overcurrent protection device. To calculate the secondary full load current, divide the kilovolt ampere rating by the secondary voltage and multiply by the square root of 3. That is 75,000 divided by 208 divided by 1.732. The result is approximately 208.1 amps. The secondary overcurrent protection device should typically not exceed 125% of the secondary full load current. In this case, 125% of 208.1 amps is approximately 260.1 amps. Therefore, a 250 amp circuit breaker or fuse would be an appropriate choice for the secondary overcurrent protection device. To determine the appropriate wire size for the primary conductors, refer to NEC Table 310.15. This table provides the allowable ampacities of different wire sizes based on the type of insulation and the ambient temperature. For example, if the primary conductors are type THHN copper conductors and the ambient temperature is 30 degrees Celsius, then a number 3 American wire gauge conductor would be sufficient to carry the 90.2 amp primary current. To determine the appropriate wire size for the secondary conductors, again refer to NEC Table 310.15. In this case, a 250 kcmil conductor would be required to carry the 208.1 amp secondary current. To determine the appropriate conduit size, refer to NEC Chapter 9, Table 4. This table provides the maximum number of conductors of a given size that can be installed in different sizes of conduit. For example, if the primary conductors are 3 number 3 American wire gauge conductors and 1 number 8 American wire gauge grounding conductor, then a 1-inch conduit would be required. If the secondary conductors are 3 250 kcmil conductors and 1 number 4 American wire gauge grounding conductor, then a 2.5-inch conduit would be required. These are just examples, and the actual calculations may vary depending on the specific circumstances. Always consult with a qualified electrical professional to ensure that the installation meets all applicable requirements. In addition to the calculations mentioned above, there are other factors that may need to be considered when designing a transformer protection system. These include the inrush current of the transformer, the coordination of the overcurrent protection devices, and the voltage drop in the conductors. The inrush current is the high current that flows when the transformer is first energized. The overcurrent protection devices must be able to withstand the inrush current without tripping. Coordination of the overcurrent protection devices is important to ensure that the device closest to the fault will trip first, minimizing the impact of the fault. Voltage drop in the conductors can affect the performance of the transformer and the equipment that it supplies. The conductors must be sized so that the voltage drop does not exceed the allowable limits. Transformer connections such as delta-delta, delta-Y, and Y-Y affect the voltage and current relationships on the primary and secondary sides of the transformer. These connections also influence the ground fault current paths. Delta-delta connections provide a path for circulating currents, which can be beneficial in some applications but can also lead to increased losses. Delta-Y connections are commonly used for supplying three-phase power to buildings. The Y connection on the secondary side provides a neutral point, which is necessary for supplying single-phase loads. Y-Y connections are less common, but they can be used in some applications where it is necessary to isolate the primary and secondary sides of the transformer. When working with transformers, it is important to follow all safety precautions. Transformers can be dangerous, and improper installation or maintenance can lead to electric shock or fire. Always to energize the transformer before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable codes and standards. Regular maintenance is essential for ensuring the safe and reliable operation of transformers. Maintenance tasks include inspecting the transformer for signs of damage, cleaning the transformer, and testing the insulation resistance. The transformer oil should also be tested periodically to ensure that it is still in good condition. If the oil is contaminated, it should be replaced. Transformers are an essential part of the electrical power system. By understanding how transformers work and how to protect them, you can help ensure the safe and reliable operation of the electrical system. Remember that this information is for general guidance only, and it is essential to consult with a qualified electrical professional for specific design and installation requirements. They can assess your unique needs and ensure that your transformer protection system meets all applicable codes and standards. Additionally, the National Electrical Code is updated regularly, so staying current with the latest requirements is crucial for electrical safety and compliance.